Minutes where we stopped in the last class. We were discussing what is known as ortho and para hydrogen. Okay, and how many of you remember what did we discuss towards the end? I hope you remember. So we are discussing this. Okay, that para hydrogen is something where you have this. Even J levels are populated. Even J levels are populated, and that combines with antisymmetric nuclear spin function, isn't it? Okay. For the para. And for the ortho, the J is odd. So odd J levels are populated, and it combines with symmetric nuclear spin functions. Okay. So ortho means parallel spin, it is anti-parallel. This is very crude way of saying things, but this is how it is. And if I calculate this, the number of ortho hydrogen divided by number of para hydrogen, how do I calculate? I just take this, divide this J odd divided by J even, but you see there's a factor of 3 coming here. Why this factor of 3? Can anyone tell me? Because this is coming from the 3 possible symmetric nuclear spin function, isn't it?
Yes, sir.
We had discussed this in details in the last class. Remember, what are they? They are like this. Sorry. What else? And what about this? We have one here actually. What is this? This is because of. I'm not writing that this is one is this, but this is because of. Can you tell me what is this? Alpha beta minus delta. Okay. So now if I calculate, if I plot this the percentage of para hydrogen, you see that as the temperature increases, in the high temperature limit, this will be something like 25%. Why? Because this ratio, if I calculate this ratio as you go to very high temperature limit, this ratio gives you exactly 3. It tells you that there are, so ortho hydrogen is about 75% and the para hydrogen would be around 25%. Is this clear? What happened to this ratio at when temperature is very small? Any idea? This ratio? What will happen to this ratio when the temperature is small? This is 0 actually, because everything will be para hydrogen. Okay, is this clear?
Yes, sir.
Yeah. So there is no ortho hydrogen. So at room temperature or slightly higher room temperature, which is around here, so if I make a plot of this as a function of temperature, so I'll get points like this. These are experimentally obtained points. Okay, and you connect this will give you a mixture. So this is actually experimentally obtained, and you will see that this is actually equal to 1/4 para plus 3/4 ortho. It matches with this ratio mixture. And I had stopped here, I did not explain it. I'll just briefly tell you why. This is because of the following reason. When the experiments were done, this is I think taken from a very old paper, long back. At that time quantum mechanics was not even properly developed. There's a guy called Denison who showed actually that, okay, who actually pointed out that when the temperature is not high, temperature is uh, mm, when there is no catalyst, this the conversion between ortho and para is not happening. So the conversion rate between this ortho hydrogen and para hydrogen is extremely slow in absence of catalyst. So in the absence of catalyst, this conversion is slow. Conversion between ortho and para. So what is done in experiment that, okay, you do the experiment, okay, say at room temperature, around room temperature, you have this mixture of ortho and para, which is 1/4 and plus 3/4, because room temperature is high enough. Is this clear? And then you cool down this mixture. What do you expect? You expect that as you cool it down, according to the temperature, there will be conversion between this ortho and para. So at each temperature, you should get this equilibrium mixture, which basically means the mixture you should get at that particular temperature, at that given temperature. It is not 75-25. It is 75-25 between ortho and para only when the temperature is high. When the temperature is low, it should be very small. And in the intermediate temperature, experimentally, people have done this is another experiment where people have shown that the equilibrium mixture has this kind of behavior, shown like here. But this is the experiment done initially where you take a mixture of ortho and para hydrogen at room temperature and you cool it down. Even if you cool it down, you see that they follow this curve, and this curve can be fitted with this 1/4 and 3/4 this kind of mixture. Okay, and if you take only pure para, it will look something like this. If you take pure ortho, it will look something like this. So only in the high temperature limit, this result will match with the other experiment, which is done in the presence of catalyst, so that at each temperature you have the conversion between ortho and para happening. Is this clear? There's another guy called Bonhoeffer and Hertrick. They carried out this experiment. So in the presence of this catalyst, which is activated charcoal, the ortho para conversion is finite. Ortho para conversion is finite. Is this clear?
Sir, could you explain which curve is, so the equilibrium mixture is?
Equilibrium mixture will come later. So this is the experimental curve. Say I have points. I just connect this with a curve. Points are experiments, these stars. So experiment you do at high temperature and you cool it down. And as you cool it down, you keep on measuring the heat capacity and plot heat capacity as a function of temperature. But
Yes.
when you did this experiment, you did not know. People did not know. You are actually all the time you're dealing with more or less this high temperature mixture, which is 75-25. You understand?
Yes, sir.
So this car can be fitted with a 75 percent contribution from the parahydrogen plus 25 sorry 75 contribution 5% contribution from the orthohydrogen and 25% contribution from the parahydrogen. This kind of weight capacity. You understand what I'm saying? CV
Yes.
would be something like 1/4 due to para, 3/4 due to ortho, all throughout this curve. You can do another experiment where you have only ortho, only para. They look like this. But later people do another experiment where they actually take this mixture and added a catalyst, say charcoal, activated charcoal, so that not only at high temperature, even at low, moderate, low temperature also, you have always the conversion between ortho and para hydrogen happening. So as a result, you'll always have equilibrium mixture. What is meaning of equilibrium mixture? It means at this time there is an equilibrium between ortho and para. So they are interconvertible. You understand what I'm saying? So interconversion is happening between these two. So that curve looks like this. and this curve matches with the other curve only at high temperature. So low temperature experiments were wrong. You understand? Because in the low temperature, the experiments were done as if with the high temperature mixture. You
Yes,
understand what I'm
sir.
saying? So this is there in the book by Mercury. You can have a look, and this is a very nice example where you use this statistical mechanics and compare your StatMech prediction of 75-25 composition of ortho and parahydrogen with experiments. This is clear. So please go and read the book by Mercury. How many of you have read the book by Mercury, by the way?
Yes, sir.
Yes, sir.
Yes, sir. Right.
Okay. Okay. Someone is asking for the link. Can you send me the? Yeah. Somebody has sent the link. Yeah. Okay. Okay. So now today we'll move to a different topic. Okay. First of all, I hope that everybody has submitted the what is that known as assignment. I think some people have uploaded but did not click the submit button. Do it now. So by tonight you submit the assignment. Okay. By midnight today, all of you. From after that, you will not get a chance. Is this clear?
Yes, sir.
Yes. I think you have submitted, Kailash.
Yes, sir.
Yes. Okay. And there are people who have not done scanned it properly. They have taken pictures and submitted. So that was not the idea. Idea was to write it down, scan that paper, then add all the papers, make a single PDF, upload it. Anyway, and click the submit button. Okay. So now today I'm going to start what is going to start what is known as quantum statistics rather, and I'm sure that it was done in 408, but not sure, but I hope it is done. Has it been discussed in 408, CH 408? Students, quantum statistics, it was there in the syllabus of,
Yes, sir.
it was done.
No, sir. I think no.
What?
Yeah. Something.
How many of you are convinced it is not done, or you don't remember? What is the answer? So now I have, say, the point is as follows, that I have n, okay, indistinguishable particles. That is my thing, okay, and I'm working in, say, let us do it in microcanonical ensemble. How many of you remember microcanonical ensemble? I hope you remember. What is that ensemble?
Yes, sir.
What is that?
Mm,
What are the macros? How do you define
And we
macrostate? N, V, and E.
NV and E, sir.
Okay, very good. So we are working in microcanonical ensemble. We have n number of, capital N number of indistinguishable particles. Okay, so they are quantum in nature. And there could be of two types. You will see, one is called Fermi Dirac, one which follows Fermi Dirac distribution. They are called fermions. And there could be another set. What is that? They follow Bose-Einstein distribution, and Bose-Einstein statistics. These are called bosons. And this is our Bose. Okay, SN Bose, Satyendranath Bose. So, who was a pioneer theoretical physicist, okay, from our country. Anyway, so we'll talk about it later, but let us write down these things. So this picture, the picture I'm going to draw today, this is extremely important. And if you remember this picture, then you can derive this distribution, okay. So this axis, the vertical axis, is your energy axis. I am calling it epsilon. Is this fine? Okay. And then this energy axis I divide into several cells. Okay. So these are single particle energy levels. Okay, so this is like I can write like here, these are called single particle okay, this is how it is. So I can think that there is I just divide into cells like this. Okay, and I say okay, in this lower cell I have some levels, so I have n1 number of levels. Okay, not n1 number, n1 number of particles, and I have g1 number of levels, g1 n1. Is this clear? So what I have is n1 particles in first cell. So similarly in the second cell I have g2 number of levels and n2 particles are there. Now what is a cell? What is cell? Cell means within that cell all the energy levels, they have the same energy value, single particle energy levels. This is like epsilon 1, epsilon 2. So what is this g1, g2? These are degeneracy factor. Is it clear?
Yes, sir.
Yes, sir.
Gi is degeneracy. So similarly, I'll have epsilon 3, epsilon 4. I am not writing, okay? You understand, no? So we are grouping into cells. What we are doing, we are grouping into that is exactly what we are doing. Okay. Now, if I take this I, Ni, what will be the answer?
N.
Of course, because the total number is n, has to be capital N, large N. Any other constant? You should also have another constant, no? What is that constant? You know already.
Sum over I Ni epsilon I Gi is equal to.
Yeah. So actually, I'll also have another like this, where it's something like that Ni epsilon I, and this is going to be E. So these are nice things because these are constraints, and you should follow this. Is this clear?
Yes, sir.
Similar things were done earlier with classical particles. But I am now dealing with particles. These particles follow quantum mechanics and they're indistinguishable. So what should be the next step? What should I calculate? You know the prescription. You have to calculate this omega NVE. What is this? If I write in words,
Partition functions. Microcanonical partition function.
yes, but let me write down in words that number of, this is number of distinct microstates, you know, accessible, isn't it? I already said, no, it's the accessible number of accessible microstate to the system under the macrostate. If I write very carefully, what is the macrostate here?
NVE.
Okay, and what will be this quantity?
Integral of the Dirac delta over the hysteresis.
Yeah, you can do like this, but we will do something else which is equivalent to that, because I have this picture. Looking at this picture, I'll do that. So let me write down and then explain. Okay. So here this W, and within the curly bracket you have Ni. Let me write down and I'll explain. This is number of distinct microstate associated with the distribution set Ni. Do you understand what I'm saying? I'll explain. So let me think. So this picture, I have drawn this picture. Okay, this is fine. How many such pictures I can draw? Anyone can answer. How many such pictures I can draw? So first of all, I have this constraint. This Ni, summation Ni is N. Summation Ni epsilon I is equal to E. These are constraint. Is this clear?
Yes, sir.
That you know. Now I have divided by single particle energy level into cells like epsilon 1, epsilon 2, epsilon 3. So if I go to this cell epsilon 1, I have N1 number of particles and G1 is the degeneracy. Now just look carefully that okay, this G1, G2, all these things are fine, but what about N1, N2, N3? Are they same? Sorry, the question should be like that. N1, N2, N3 are arbitrary, isn't it? In this picture, maybe I put 70 particles here, 40 particles here, like this, isn't it? But I can have another picture where I put, say, 60 particles here, 50 particles here, isn't it? It's a possibility. What do you think? So N1, N2, N3 all are going to vary. But how can I vary? Okay, keeping this constraint, N1 sum over Ni is equal to N, I can vary N1, N2. Also have to keep in track that I cannot violate this constraint, the other constraint. So if I follow both if I keep both the constraints, if I obey both the constraints, then many ways I can have this distribution. So I'll have within curly bracket Ni means Ni would have a set of distributions. Is it clear? So this is like different pictures. So I have drawn one picture where I put N1 here, N2 here like this. In another picture, I can put Ni prime, N2 prime, isn't it? Another picture, N1 double prime, N2 double prime, whatever. These are dummy variables. You understand? This N1, N2, all these things. So essentially, for a given picture, I have a given distribution of Ni within curly bracket. Is this clear?
Yes, sir.
Yes, sir.
Okay, and now the total number of microspheres are what? I will do all this permutation, isn't it? All possible permutation with this constraint, these two constraints, isn't it? So I should actually take this W, which is for a given Ni set, for a given distribution set within curly bracket Ni, and then I sum over all possible permutations of Ni, all possible distribution set Ni within curly bracket. Is this clear? I should sum it over all possible arrangements of Ni's. Please get it clear. This is very important. Very, very important. Is this clear? Just and
Yes, sir.
and when I put the sum, I put a prime here. Any idea what is this prime?
Constraint.
Yes. Due to constraint. I cannot take like a sum which has no constraint. You have constraint. What are the constraints? I can call it equation 1, equation 2. These are constant.
Yes, sir.
So keeping that in mind, so because of that, I put a prime. Prime means I know that okay, whenever I take the sum, I have to follow these two constraints. Okay. Is this clear? This is very, very important. What I have written here.
Yes, sir.
See, I am telling you, if you go back and read a book, it is very difficult for you. Not for everyone, but for some people, I'm sure it will be difficult for you to understand. So please If you have queries, you ask me. So I give you n number of particles. I give you say 10,000 particles, and then you distribute with this constraint. But you can have many distributions, no? So it is sum over all possible distributions. So all possible set of ni. Is clear? Okay. Okay. Is it clear? Then I move to the next part.
Yes, sir.
I think it should be clear now. The next part is whether I can write W. I can express W in terms of something else. And this one I am writing it like this. Small w. Do you understand what I have written here? So let me write down. So what is important here, students? See, this picture is very important. Is this clear? This picture. So don't forget this picture. How do I? Okay. No, I should not do this. Yeah. This picture is important. Okay. Now, what is omega I? Small omega I, small omega I. Omega or small w, whatever. I think it is omega. This is, if I write down, you'll understand. This is the number of distinct microstates again. Associated with ith cell of the spectrum. So the cell contains how many particles?
Ni.
Ni.
Yes. Ni particles
Gi level.
to be accommodated among GI levels. You understand what I'm saying? So it's like each segment, this one, this one, this one, like this, isn't it? This segment, like omega 1, omega 2, small omega 1, small omega 2, small omega 3, like this. Is this clear?
Yes, sir.
Yes.
And this product goes over what? This is
All
the
right.
product now. Goes over all the cells in the spectrum. So this product goes over all the cells in the spectrum. Okay. So if I give you this picture, you look at this picture, you divide the total W into a product of small w's, isn't it? And the earlier picture is that I have this picture, but I have several of these pictures. So in that case, it will be the omega will be sum of all several those pictures. You understand? Here it is a sum, but here it is a product. For a given distribution, it is a product because you have divided into cells. This is like a product, but you have many possible distributions. So the total number of microstates would be a sum of all possible distributions. Okay, sum of all distinct microstates. Is this clear? Because this is very important for this class.
Yes, sir.
Yes, sir.
So this is fine. So I can always write that this omega I, this small omega I, small w or omega I, is the number of distinct ways. Sorry for this handwriting because I have a lot of problems writing here. In which the Ni identical and indistinguishable particles can be distributed among the GI levels. Is this fine?
Yes, sir.
This is omega I, yeah? Okay. So once you understand this, no, then it is not very difficult. So now next we will do, so let us assume that I have n number of, capital N number of particles which are fermions. So they form Fermi Dirac distributions. They are fermions, follow what is known as Fermi Dirac distribution. We'll see what is that Fermi Dirac distribution. And you know that in that case, what will happen, that this Ni, what are the possible values of Ni? 0 or 1. This is for fermions, okay? Either the level has one particle or there is no particle, okay? You cannot have more than one for fermions. I think everybody knows it here, okay? So what will be then this omega for Fermi Dirac distribution? See, it is like what?
Is it JICNI?
Yes, it has been like it is like that, because you have Ni, so it is fermion, so which basically means, isn't it,
Yes, sir.
for fermions? For fermions, it is like this. So for Fermi Dirac, this is going to be, you remember, is going to be Gi factorial divided by Ni factorial sorry, this factorial, huh? Is fine?
Yes, sir.
And then what will be the capital W? The big W. This is a product of okay?
Hello, sir.
Yes.
So please could you explain again the fermion, this distribution?
Yeah,
How-
fermion means in one of the levels, I have either I can have one particle or no particle. So if I go, for example, if I go to this cell, I have G1 number of levels, N1 number of particles. So G1 has to be greater than N1, isn't it? The base thing could be that G1 equal to N1, the number of particles is equal to the number of levels, isn't it? You cannot have a situation where N1 is more than G1, no? For fermions,
Yes, sir.
that is how it is. So Gi
Oh,
for any given I has to be greater than equal to Ni. The base thing
got,
is Gi equal to Ni. So
got
then
it.
this is how you distribute. And you take a product of that, that will give you the capital W. Okay? So now next I go to what is known as Bose-Einstein. or bosons, they follow what is known as Bose-Einstein statistics. Now, what are the possible values of Ni in this case? Could be 0, could be 1, could be 2, could be 3, any integer, isn't it? And what is possible value of Ni max? It could be actually capital N, but I can assume this is N if as you go to the thermodynamic limit. Okay, this is how it is. So I would expect that BE statistics, which I will derive, will allow much more or much more number or much larger number of configurations than that for FD, isn't it? While satisfying same constraints. Clear? If my this statement.
Yes, sir.
So let me illustrate how to do it. For example, I give you 5 particles, okay, and there are 3 cells. So one arrangement like this, the cells I'm calling it box 1, box 2, box 3. So I have 2 particles here, 2 particles here, 1 particle here. Okay. So Ni is equal to whatever 5. What is the value of Gi here?
3.
3. This is one possibility. Now, how can you get other possibilities? So that can be generated by moving sticks. What are these sticks? Any idea what are these sticks?
The partition of boxes.
Yeah, these are sticks. Okay. Boundary. How many sticks are there? In general, you'll have like Gi minus 1 number of sticks. Is this clear? Remember, these balls are indistinguishable. They are all blue, for example. Okay, because they are quantum particles.
Yes, sir.
So what you have here is actually Ni number of particles plus Gi minus 1 number of sticks. So total this number. So this number of things, because arrangement means what? You can change the number of particles in general, and you can change number of sticks, things to be arranged to generate configurations while arranging a given ni among themselves. Okay, I don't know. Does not create any new configurations anyway. So whatever, but what will be the WBE then? If I follow like this, you can small WBE or omega BE. You understand that total n is total number of objectives things is this factorial of that, and I divide by, tell me.
Ni factorial bi minus 1 factorial.
Yes. Okay. And in this case, when your Ni is 5, Gi is 3, what will be this value?
7 factorial.
Yeah, it is going to be like 5 plus 3 minus 1, 7 factorial divided by 5
5
factorial,
factorial into 2
2
factorial.
factorial. And if you calculate, this is 21. So actually there are 21 possible arrangements. So there are this possible arrangement, no? So possibilities. And it is obvious that with the same constraint, bosons will have more number of possibilities than fermions. Okay. Bosons will have more number of possibilities than fermions. So I can give you another example. For example, if I take, say, Ni2 and Gi3, what will the omega be for this? You can do this calculation. This is going to be 2 plus 2, 4 factorial, divided by 2 factorial, 2 factorial. What is the answer? Answer is 6. But with the same number of particles and Gi, what is the value for Fermi Dirac? You know the Fermi Dirac distribution thing, which is Gi factorial divided by Ni factorial, Gi minus Ni factorial. So what is Gi factorial? Gi is 3 factorial divided by Ni factorial, and then you have Gi minus Ni, which is 1
1,
factorial. What is this answer? Is
3.
less than Bose-Einstein. Isn't clear?
Yes, sir.
So now what happens? What happens if you have classical particles? Next thing. The classical particles are distinguishable. You can color them. Okay. So basically, what I can say that Ni particles, if the particles are classical, may be put into any of the Gi levels. Independently of one another, of course. And the resulting states may be counted as distincts. Basically, you understand what I'm saying? What I'm saying that you have Ni number of particles and Gi number of levels. How many states are possible if you have this?
Bi power ni.
Yes. So it should be like this. Then the Sorry. It has to be what do you say? Basically, the number of Ni. This is fine. But you remember that if you have n number of objects and you have group into n1, n2, n3, remember this one, no?
Yes, sir.
For distinguishable particles. So this has weight factor is what? This weight factor is actually this. Which is and then it essentially tells you that your for classical particle, which is Maxwell-Boltzmann, it's nothing but Maxwell-Boltzmann. This is going to be product of so this is your for the classical particle, Maxwell-Boltzmann. Because these are number of states are like gi to the power ni, but each state would have a like weight factor like this 1 by ni factorial, and then you have independent states, you have to take a product of that. So it's like that. Okay, so this is how it is for the classical particle. Okay, what should be the next thing I should be doing? Any idea? Now you know what is the next step. Tell me, what should I calculate now?
Entropy and maximum.
Entropy. Yeah, you should calculate entropy and maximize entropy. That is should be done, no?
Yes, sir.
So entropy calculation. Hey, others should also tell me, how do you calculate entropy? Hope others are listening.
Yes, sir.
Yes. How do you calculate entropy?
By derivating partition function.
Yes, for microcanonical is very easy. S is
Log omega.
ln.
Yes, sir.
What will be the next step? KB ln. You understand, no? I'm just putting it here. And this is approximately equal to, and that is what I'm going to do is this. You understand this?
Cradle point approximation.
Yes. So basically, it is approximately equal to the logarithm of the longest term in the sum, isn't it? Remember the most probable.
Yes, sir.
Okay. So basically, I have a particular distribution of ni, which I'm calling ni star. So it's a distribution set that maximizes the number and Ni star is the most probable. Ni, isn't it?
Yes, sir.
Yes, sir.
But don't forget the constraint. So you have to go along with the constraint. So you have to go along with the constraint. Is it clear?
Yes,
Yes,
sir.
sir.
So what I'm going to do, I'm going to employ,
Lagrange multiplier.
yeah, method of multipliers. Okay, but with the constraint. So what will be the answer? Actually, I'll have something like take a log of that. No, it is ln w ni minus alpha. If I write like this, dni beta epsilon I dni to 0. Okay, and you know that delta L W ni, the capital W ni is sum over delta L small wi ni, isn't it? Logarithm, no? The product becomes sum. Because capital W is a product of small w's. So log of capital W is a sum of log of small w's. That's why, isn't it? Okay. This is what I'm going to do today. Any question? When I do, it will be clearer. So let us do for the Fermi Dirac distribution first. Statistics. What is the expression for FD? Small w
G factorial upon
divided by
n factorial G.
yes.
G minus n factorial.
Okay. So let us take ln of WFD. Again, I'll make use of Stirling approximation. Sorry, it should be minus. N minus n. Is this clear? Am I doing anything? I think it should be okay.
J minus Ni.
Yeah, the other way. Okay. Wait for a minute. It's taking some time to Okay. So can I cancel few things? I think I can cancel, no? What I'm going to get here? I'm going to get here is gi is here, gi is here. So I can take minus gi common. I'll do like this. Minus gi. Now ln minus gi ln. You have ln, so ln gi minus ni divided by gi, ln gi. So it's going to be I hope you follow. Please tell me whether you are following.
Yes, sir.
And if I take ni common, which is here, it will be ln gi minus ni divided by ni. So what I'm going to get? I'm going to get ln if ti is equal to minus gi ln 1 minus ni by gi plus ni ln gi minus ni minus 1. Fine?
Yes, sir.
I hope this is fine. This is for Fermi Dirac. Now let us do the same thing for the Bose-Einstein. If you have a pen and paper, you can do it. What is Bose-Einstein W? You remember? It is
Ni plus gi minus 1
ni plus
factorial.
gi minus 1 factorial divided by
Ni factorial gi minus 1 factorial.
yes. If I take a log of this, what I'm going to get? I'm going to get log. You know that I can. Okay, let me write down first. The first term is okay. Is this fine? Next term is this clear up to this? This should be fine, no? If I have not done anything wrong with the sign, I hope I have not.
And that will be a minus gi minus 1 log gi minus 1.
Which one? This
Second term from the right. The second last one.
this one.
gi
This one.
minus 1 ln gn minus 1.
Yeah, yeah. It is minus, no?
Yeah.
So the problem with this eraser, it takes a lot of time to come. Because it will be minus gi minus 1 ln gi minus 1 n ln minus n. Then minus, it should be like this, no?
Yes, sir. Yes, sir.
And then it should be like this. So what can I do? I can now also, you see that degeneracy is usually very large. gi minus 1 is like gy. Okay, so this one you can say, okay, this is approximately equal to you can
Hello,
say
sir.
yes.
Sir, I think so. You left the Stirling approximation for the first term. You left the second term for that.
Yeah, yeah, n ln minus n, no?
Yes.
Yeah, this will be useful because this is going to cancel this, 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 and this. No, I'm going to cancel. So this one is going to be equal to what I'm saying, that okay, if I take ni common, first of all I can take ni common. If I take ni common, what I have is you have ln ni plus gi minus 1, because this term, isn't it, divided by ni, isn't it? I should have one term like this. We'll do this later. Okay, plus you take gi minus 1 common, then you'll have ln ni plus gi minus 1 divided by gi minus 1, isn't it? And then I make use of this. So this will be something like ni ln 1 plus gi by ni, because gi minus 1 is gi, plus gi ln ni by gi plus 1, isn't it?
Yes, sir.
So this is the final expression for my Bose-Einstein distribution. So in general, I can write something. What will be the in general expression? So let me write down like this. In general, ln of any small omega I is ni ln gi by ni minus a minus gi by a ln 1 minus a into sorry this yeah ni by gi. This is general expression. Okay, why it is general?
A is -1 for, I
Yeah,
guess,
let us go back. Let us go back. Not this one. Like I want to. Yes. Yes. Copy and paste it. Oh. I think I have to do it properly. I want to just copy this. Copy. Okay, this is for FD. Similarly, I'll have the same expression, similar expression for B. This is FD, no? Similarly, I have an expression for BE, which is this. Now, can you tell me in what will happen here? If I compare this, if A is -1, what do I get? If I put A equal to -1, see, have a look.
Bose-Einstein.
Yeah, I'll get B. And if A equal to 1, what do I get? Just see, because if A equal to 1 is this is 1, what am I going to get? Fermi Dirac, isn't it?
Yes, sir.
And if A equal to 0, what I'm going to get? This is Maxwell-Boltzmann. Can anyone see? You can double check it. Just in the Maxwell-Boltzmann, the small wi, remember, na? It is gi to the power of ni divided by ni factorial. So ln w Maxwell I is ni ln gi minus ni ln ni plus ni, isn't it? So if I take ni common, what I'm going to get? If I take ni common, what I'm going to get is ln gi by ni plus 1. Okay, fine. Okay, fine. Is it fine?
Yes, sir.
Substitute A equal to, is that gi by A in that log omega I expression second term?
Which one? Here? Yes, gi by a. Gi by a.
And how do we substitute A equal to 0?
So you don't do. You just take a law. You just take a
Limit.
limit. Essentially, take a limit, because what you have is here ln 1 minus x. You know that when x goes to 0,
Tends to x.
it is equal to what? It is minus x or x. Tell me. Ln 1 minus x equal to, when x goes to 0, ln 1 minus x. What happens to that? You understand, no? Ln
Yes,
1
sir.
minus x, when x goes to 0, what do you get? This term.
Yes.
So can anyone tell me what is log expansion of log? Tell me. This is equal to what? Tell me.
Minus x, sir.
Minus x.
Yeah.
Good. If it is minus x, then this term ln this will give me,
Minus x.
isn't it?
Yes, sir.
And then you have the prefactor. Prefactor is what I'm going to get? A will cancel, Gi will cancel. It will give you Ni. This Ni, no? Ni into 1 is Ni, no? Matching. So just to check. But we'll be dealing mostly with Fermi Dirac and Bose-Einstein. Is this clear so far?
Yes, sir.
Now next thing what I do this I carry out this variational principle calculation, no? Essentially I take a derivative of log of omega I with that constant with respect to Ni, isn't it? This is exactly what I do. This expression. this expression I take it so this is the expression, and the next thing what I do this del ln I, which is basically means I'm taking derivative with respect to ni. What is the first term? 1 into ln. What is the next term?
Ni by gi by ni minus a.
Into
Minus gi by ni square.
into, okay. And next time is into 0, sorry, it is minus actually. I hope I have not done anything. Of course, you have.
Gi by a.
Huh? What?
Gi by a times 1 by a.
Sorry. And because gi by a I have not written, no, this one I have written ni. This one, no?
Yes.
Yeah. Gi by a. Now, this is the expression, no? Now I can just simplify it further. If I simplify, what I'm going to get is as follows: ln gi by ni minus a. What is the second term? Look at carefully. This one is minus. Look at this. This term. You look at it.
Ni will
So just
cancel
look at it. Minus is there. Minus gi by ni square into ni. So it is actually gi
by ni.
ni
Ni
1 by
gi by ni minus a.
minus a. And what about the next term? Next term is plus.
Plus,
But a cancel, gi will cancel, isn't it?
yeah,
What I have is this. But what is this term?
Equal to the.
Yeah,
before it.
Shantanu, you have a lot of noise coming. Yeah. So this is, see, this is nothing but if I multiply this, it will go 1 minus a into gi by ni, isn't it? Okay, is this clear?
Yes, sir.
Because I have forgotten to write this, no? Gi by a, no? So they are identical, no? These two terms? There has to be, they have to be identical. Is it?
The gi by a has cancelled, right?
Cancel, no. Yeah. So, no, that has cancelled. You're right. So I have this, gi by a has cancelled. Something else will cancel, no, here?
Yes, sir. If you simplify the second term, you get the.
Yeah, because this is multiplied, it will be gi by ni. It will be, okay. I take gi by ni common, this will cancel. It will be 1 minus a into ni by gi. So they will cancel, no?
Yes, sir.
So they're going to cancel. This I want to be sure. So what I have here is ln gi by ni minus a. Okay, but don't forget about the constraint. I did not put the constraint. Once you put the constraint, I'm going to get this one is there, but you know that this one is there. This is omega I, no? So basically, you know, the capital W ni is sum over this, no? in general. It is also Ni.
Yes, sir.
So what I'm going to get? I'm going to get, if I put this constraint here, what I'm going to get is as follows. I'll have this, but you'll have a sum of this, no? What else?
Delta Ni.
Also I have this, isn't it? Because alpha minus
Minus epsilon
beta
I.
epsilon I into, but it should be true for any arbitrary value of a, no? Del Ni.
Yes, sir.
What does it mean?
Multiplying term is 0.
It basically means that del Ni is multiplied with some term and sum over I. So each term in the sum is 0.
0.
Which basically means that I can write ln gi by ni minus a minus alpha minus beta epsilon I is equal to 0. Fine? Or ln now whenever I write ni here, but ideally I should write what? I should write ni star, isn't it? In other words, my ni star, the most probable ni, is actually gi. Now a equals to 1 for, remember, for what? Which one? A equals to 1
Fermi Dirac.
for Fermi Dirac. Fermi Dirac. So ni star Fermi Dirac is equal to gi divided by 1 plus a equals to minus 1 for Bose-Einstein, no? Isn't it? It is for the
Yes, sir.
Bose-Einstein. Now, if it is Bose-Einstein, then ni star Bose-Einstein is equal to gi divided by minus alpha plus beta epsilon I minus 1. And a equal to 0 for Maxwell-Boltzmann. But this is, you can see directly, no? What is going to be gi?
E power minus alpha plus beta epsilon I.
Okay, and in the next class, we'll see what is the value of beta and alpha. Beta you can guess is 1 over kVt. Alpha you can also see what is going to be. Alpha is also going to be something. Okay, so we'll stop here today. I think because I don't have time to start something new today, but we'll stop here. But I'm sure that it was done in 408. I'm very surprised to know it is not done. Kailash, are you sure it was not done?
Yes, sir.
So how many of you knew about it? These distributions.
I didn't knew.
So we have
Without-
done
Sir, we have read it, but not very
Who
deeply, sir.
who is this? Who
Sir,
is this?
Ravi Maurya, sir.
Okay, where? During your BSc?
Not sir, BSc, just due to curiosity.
Okay, very
Yeah.
good. And who else? Somebody else said something, no?
So we UGs have done it briefly in first year physics.
Physics, yes, yes. PH 107, no?
Yes, sir.
It was done like this, maybe. I'm not sure. Must be like this.
Not so much in detail, but yes.
Yeah, so we'll start from here in the next class. So by tonight, please submit the assignments. Okay, very important that you submit the assignment by tonight. Okay, very important. Don't delay things. Okay, I hope you are following the course. This point, it's a little heavy course, I know,
Yes,
Yes,
sir.
sir.
Following.
but serious business of statistical mechanics. So I have to go like this. No, I cannot take any formula for granted. I have to derive things, isn't it?
Sir, can we have a tutorial class before
Yeah,
exam
we'll have.
for assignments
We'll have.
for few questions?
We'll have. We'll have.
Assignment.
We'll have. We'll have. How many classes are there before the mid sem?
I think 3 more classes will have.
So we can convert one class into this. The last class we can convert this into tutorial. Okay. Okay, that will be nice. We can convert the last.
2 more left.
2 more are there.
Thursday and Monday.
Okay. Okay, we'll see. I'll try to finish because I cannot go very fast. Okay, the kind of thing I am teaching. If I go very fast, it will be difficult for you to follow. Okay, I'm stop recording.